Hey, everybody. So we're going to continue with our parade of identities, and we're going to look now at what are called the double angle formulas, and the reason why will be pretty obvious in a moment. And so the way we get these is we start with the sum and difference angle. So let me just show you what I mean. If you remember the sum angle for sine, we figured out last time that the sine of alpha plus beta is equal to the sine of alpha cosine of beta plus the sine of beta cosine of alpha. Okay, so that one we worked out last in a previous video. If we start with that and we wonder what happens if those two angles are the same, that is, what if alpha is equal to beta? Right? And I'm going to use the symbol theta for both of them, right? So it's one angle, I'm just going to use theta for this. So that means our sum now looks like theta plus theta. They're both the same, but the rule still applies. It doesn't say that they have to be different. This relationship still holds. So this is sine of what was alpha, which I'm calling theta, and beta, which is the same thing, which I'm calling theta. And so over here, we get theta cosine theta. Well, we can write this much more simply. This is sine of 2 theta. Notice on the right, those two expressions that we're adding together are the same thing. So there's simply 2 of them. And this is a really nice formula that we have here. In fact, let's collect all the double angle formulas over here. Double angle formulas. So we have one for sine. Sine of 2 theta is 2 sine theta cosine theta, right? So remember what these do for us. They give us a way to evaluate angles that we might not be able to otherwise, right? If they're not something from the unit circle. But that's more of an exercise to get used to them. More importantly, they, at least to my mind, they let us have some algebraic tools, right? So if we have an equation, if we have a function involving sines and cosines, it might be really convenient to be able to manipulate them in this way. And it's really hard to describe some of these things. A lot of these tools are going to become really useful in calculus and other later courses you might take. Kind of like how you have to learn algebra before you start learning functions, right? Or multiplication before you learn algebra, right? We're building tools for stuff you're going to use down the road. We can do the same thing with cosine. Cosine of theta plus theta. So again, I'm using the sum formula for cosine. It looks a little bit different. You end up with cosine of theta minus sine theta sine theta, right? In the original, this is alpha plus beta, and you get alpha, beta, alpha, beta. But since they're both the same, we get this special case of the sum formula, where if we simplify this, we get cosine of 2 theta is equal to cosine squared theta minus sine squared theta. Right, so let's put this one up here. Cosine of 2 theta is equal to cosine squared theta minus sine squared theta. Using the Pythagorean identity, remember this is the identity that tells us that sine squared theta plus cosine squared theta is equal to 1, we can rewrite this in 2 different ways. I could write that sine squared theta is equal to 1 minus cosine squared theta, right? That's an equivalent statement. Or cosine squared theta equals 1 minus sine squared theta by just subtracting it. Well, with these 2 substitutions, we also get some convenient identities. So if I take sine squared theta and replace it, so in if I replace this sine squared theta with 1 minus cosine squared theta, I get cosine squared theta minus 1 minus a minus cosine squared theta. So we end up with 2 cosine squared theta minus 1. If we go the other way, if we replace cosine squared theta with 1 minus sine squared theta, then we end up with cosine of 2 theta is equal to 1 minus 2 sine squared theta. And these are added to our list. All right, so each of these is equal to, ooh, my writing is really not straight when we look at this horizontal line. Cosine 2 theta, these are all cosine of 2 theta, right? And so I also want to point out that, right, you could keep doing manipulations like this. We have lots of things. You could take that cosine is equal to 1 over secant theta and make that replacement and get a new identity. The ones that we're listing right now are the ones that the mathematical community has determined come up the most, right? And there's no point in, there's a, you know, we could keep doing this forever, coming up with identities by doing different substitutions, but there are some that turn out to be useful often, and these are on that list. So finally, one more that we get for tangent, and this again is using the sum formula. I'll skip straight to the end. We get tangent of 2 theta equals 2 tangent of theta over 1 minus tangent squared theta, right? And we get it in much the same way. We will you take the sum formula for tangent, take the sum formula for tangent and let the two angles be the same angle, and you end up with this formula. So this set of formulas are known as the double angle formulas, okay? So let's do an example with these. As all of these, it's really, whenever we apply formulas, it's just making sure you identify to yourself, all right, what's theta in my problem, so that you know where, in this case, if you're doing sum angles, what's theta, or alpha, what's beta, what's playing each role, and putting everything in the right place. So let's do an example that's also going to show us a couple of common errors, not particular to these rules, but this is a good opportunity to show them. So let's do this. Suppose we know that tangent of theta is equal to -3/4. And theta is in quadrant 2. Let's find sine of 2 theta. Okay, so the first thing I'm going to think to myself is, okay, I know something about tangent of theta. I want sine of 2 theta. This is an obvious case where maybe the double angle formula makes sense, right? So I'm just going to write it here for myself for reference. Sine of 2 theta is equal to 2 sine of theta cosine of theta, right? That's the formula from up above. So now the problem hinges on, can we find sine of theta and cosine of theta? Okay, so we've got information about tangent. How do we get there? Let me point out an error. This is a common error. We know that tangent of theta is equal to -3/4, and we know that tangent of theta is equal to sine of theta over cosine theta. That's true. These two things together, sometimes people try to make this mean, oh, that means sine of theta over cosine of theta is equal to -3/4. This is also true. So far, so good. Here's the mistake. Going from this to concluding then that sine of theta equals -3 and cosine of theta equals 4. Okay, there are a lot of problems with this. Okay, so let me make sure we don't mistake this for truth. This is not true. First of all, we know sine and cosine are never larger than 1 or smaller than -1, and both of these break that. And even without that restriction, in general, it's not the case that if I tell you a over b equals, let's say, 1/2, this does not imply that a equals 1 and b equals 2, right? We can think of an infinite amount of numbers that when you divide them, you get 1/2. All this statement says to us is that whatever value sine is and whatever value cosine is, when you divide them, the ratio is -3/4, right? So if we didn't have the restriction about bigger than 1, it could be -300/400 or 300/400. Those wouldn't work for sine and cosine. They're too big, but they would work just for numbers that give us ratios of -3/4. In the case of sine and cosine, they're going to have to be numbers smaller than 1. So we'd have to find some, right? If I took the ratio of, here's some contenders, 3/9 over, or -3/9 over 4/9. This would equal -3/4. These numbers don't work for signing this particular problem for other reasons, but I'm just giving an example of numbers that give us this ratio. Okay, so we don't want to make that mistake. So how do we solve this problem? Well, I'm going to do it in a couple of different ways. Let's do it one way. Call this solution 1. Let's use a triangle and then see if we can translate that triangle, see how that relates to the unit circle. Okay, so there's a couple ways to use what we know about triangles, and oops, that's not a triangle. That's a triangle. So if this is theta, all right, the opposite side is tangent of theta is opposite over adjacent, so this is -3/4. And well, when we're doing distances, we usually don't think about the negatives. I'll get back to that in a moment, what we'll do with that. And if you do the Pythagorean theorem, it's easy enough to see that 4 squared plus 3 squared is indeed 5 squared, so that hypotenuse must be 5. Now, it feels a bit like I'm making the same mistake I made a moment ago of saying, wait, the ratio is 3/4 doesn't mean the adjacent side over the opposite side over the adjacent side has to be 3/4. Okay, that's true. I could have chose the numbers 6, 8, and 10, or 3/2, 4/2, and 5/2, right? Any 3 numbers. The point is, the triangle remains in the same proportion. The ratios are the same for all of those, right? In each case, what's happening, if I were to right, so if I scale this triangle and make it twice as big, right? Well, of course, this is now 10, this is now 6, this is now 8. The ratios stay the same, and that angle is still the same, right? These two angles are exactly the same. And so we can take, in terms of figuring out the ratios, we can take any scaled version. There's kind of like a primary triangle that makes this make sense. And we can scale it in any direction, bigger or smaller, and we'll get all the same ratios, even though the sides are different. So this works out. So 3, 4, 5 is a nice, easy one. I just chose the easiest I could pick for this ratio, right? Using the 3 and the 4. I'm not going to worry about the negative yet. That's gonna be solved by this part of the problem. But this triangle will give me the proper ratios, and I'll make this clear on the unit circle in a moment. So in this particular triangle, sine of theta equals opposite over hypotenuse, and cosine of theta equals 4 over 5. Okay. However, these are technically not true, or I don't know if they're true quite yet. I have to think about quadrant 2. I have the correct ratios, but not necessarily the correct sign, not sine and cosine, sign like positive or negative. So I just have to look at my unit circle. I don't even really need the unit circle, just looking at quadrant 2. I know that cosine's negative because we're to the left, and sine is positive because we're above, right? So cosine's negative when we're to the left of the y-axis. Sine is positive when we're above the x-axis. So it must be these two ratios, right? Sine is 3/5, cosine is negative 4/5. So now we know that sine of 2 theta is equal to 2 times sine 3/5 and cosine negative 4/5. And what do we end up with? 2 times 3 is 6 times 4 is 24. And we have a 25 in the denominator, and there's a negative floating around. So sine of 2 theta is 24 over 25. Also notice tangent of theta is equal to sine over cosine. So this will be 3/5 over negative 4/5, which indeed gives us the ratio negative 3/4. So there's that example of the ratio is 3/4, but it does not mean that sine is 3 and cosine's 4, with one of them having a negative. Okay, that is our answer. Well, that didn't work. Let's try one more time. I guess I don't really need it to be straight, so I'll just stop. Okay. I do want to show you another method. I also want to make one more point about this. Another way to think about what we did here. Let me just relate this triangle to the unit circle. All right, so here's a set of axes. Let's throw a unit circle on there. Let's try to get it centered at least a little bit. All right, now let's grab this triangle. And I'm going to shrink it. I'm going to resize it a little bit. I want to shrink it down so that its hypotenuse is 1. In other words, I'm going to make it 1/5 the size. Well, how do I know when it's 1? I'm going to use my unit circle. I'm assuming that's 1. I know my scale's not perfect. This isn't actually 1/5 the size, but let's just pretend it would get too small. So there now the hypotenuse is 1. Okay. So what does that mean happened to all those numbers, all those lengths? Well, they're all going to shrink by 5. So 5 becomes 1, 3 becomes 3/5, 4 becomes 4/5. And so here's that triangle fitting into the unit circle and giving us those values of sine and cosine. Now, I'm not sure if I can flip this thing. I don't know if my software lets me. Try one more time. All right, never mind, that doesn't work. Well, if you imagine reflecting this, I can just draw it. If you reflect it horizontally, we get the same triangle. Let's all pretend that that's the same triangle with those same dimensions. We could, oops, I accidentally shrank it as I moved it. Okay, more or less that's the same triangle, right? Obviously, if we reflected it perfectly, we would. And those distances hold, but we notice when we put them into quadrant 2, the coordinates here, the horizontal coordinate is still, or distance is 4/5, but it's in the negative direction, and the vertical coordinate is 3/5. So this is the nice way we can use we can use triangles to still help us out with the unit circle, right? It's all that triangle stuff still applies, but we just have to be a little careful how we think about it. If we were in quadrant 3, we could flip that down, and then in quadrant 4, we could take the other one side and flip it down. We have the same triangle, the same distances, just getting different positive and negatives. Okay, let's do one last thing, just as an alternate way to think about this. Let's go back to, remember we had tangent of theta equals -3/4, and we were looking for sine of 2 theta, which is equal to 2 sine of theta cosine of theta. And we determined before that because of this relationship about tangent, we know that this is true, right? Well, I can rewrite this as sine of theta equals -3/4 cosine of theta, right? I'm just multiplying cosine to the other side. It's another way to think about what this ratio means, that the numerator is 3/4 as big as the denominator. Now, if I take the Pythagorean identity and I use this substitution, I replace sine with -3/4 cosine. This whole thing is squared. Remember, this squared here is really unfortunately written. I don't like this notation, but it's used universally, so I have to live with it. What do we end up with? Well, when we square this thing, we get rid of the negative. We have 9/16 cosine squared theta plus cosine squared theta equals 1. If we add these two together, this is 16/16 cosine squared theta plus 9/16 cosine squared theta. So we'll have 25/16 cosine squared theta equals 1, which means cosine squared theta equals 16/25, which means cosine of theta is plus or minus 4/5. Since we're in quadrant 2, where cosine is less than 0, we know that cosine of theta is -4/5. And then if we use the relationship we started with, that sine of theta is -3/4 of cosine theta, but cosine theta is -4/5. This works out to 3/5. And those are the two answers we got above. We can put them in here to get our 3/5 times -4/5. What did we say it was? 24/25 negative. Okay, same answer, of course. The Pythagorean identity is just the same idea we're doing geometrically up there, done in an algebraic way. Both of these are appropriate, and you should probably understand how to do both. They're both good ways to be able to look at this problem. Okay, that is it for this one. Thanks, everybody. I will see you next time.